Hi, my name's Charles and we're Group 13. We consist of myself, Mohammed, Kevin, George, Greg and Cameron, and this is our presentation on low emission ship design.
We used a Gantt chart to govern the schedule of our activity to produce our design and presentation on time.
The ship has several stakeholders and all of their needs and wants must be met for the ship to be a success. Customers need a ship that will run at the same timetable as the predecessor. Customers must also have a pleasant and enjoyable experience whilst travelling with us. The local residents and businesses want a ship that doesn't affect them any more than the previous vessel. Also, other pressure groups could be very interested in what materials we'll be using and what effect they'll have on the environment. The government has laws and regulations that the previous ship met which allowed them to operate in the bay. Our ship must also meet these. Employees are another key stakeholder and must have a safe and comfortable place of work. The owner wants a ship that will reduce its operating costs and improve service to increase their profit margins. Other harbour users don't want to be affected any more than the previous ferry, so the new ferry can't make too much noise and can't produce a large swell.
The current ferry has an efficiency of 83 kilowatt hours per kilometre and a power output of 1,120 kilowatts. The ferry is only refuelled at night and uses full diesel engines to power its propellers. The ferry makes 25 round trips a day, each with a journey of 6.48 kilometres.
Our brief was to stay within the size of the current ship, meaning that our maximum dimensions were a length of 34 metres, an overall beam of 12 metres, demi-hull beam of 3 metres, draft of 3 metres, but an unrestricted height, bearing in mind that a taller craft would be more unstable. We also had to stay within the turnaround times of the current ships. We also had to stay within the current passenger capacity, which is 385 passengers, bearing in mind that if we increase this, it would strain terminal efficiency. Our ship also had to be 50% more efficient than the current ones. We also had to think about not impacting the surrounding area, and so reducing swell impact and reducing noise pollution.
In total, 5 materials were considered for the ferry's hull, including the existing vessel's aluminium alloy. The only true sustainable option was timber. It offered a high strength to weight ratio, very good durability. However, the very high expense proved it to be not favourable. Glass reinforced plastic had a very low strength factor, and with the hazards in production, again not desirable. Steel, good strength, but far too heavy, having an effect upon the overall power consumption of the vessel. We then considered the properties of the aluminium alloy and fibre reinforced composite material. Both had very similar densities, although the fibre reinforced composite had much superior strength. The plus point of the aluminium alloy was much less energy in production, with a melting point of 588 degrees Celsius versus the FRC of 1725. This was by the volume of material. The aluminium alloy was also cheaper. However, the fibre reinforced composite offered the option of less material with still maintaining the strength factor. Although this may not have been enough to compensate the energy consumption, we thoroughly believe that savings would have been made during the service life of the vessel over the 30-year period. The FRC was easier and quicker to repair, and also we believe that at the end of the service life of the vessel that the recycling industry will have evolved and therefore enable the FRC to be much more favourable for recycling in future years. The higher cost of the fibre reinforced composite material was considered, however believed to be very much compensated by the overall fuel savings of the vessel, as the lower weight factor would create a much lower demand for fuel during its working life.
The seating will be made of a box section steel frame and upholstered foam padding. It is cheap, comfortable, lightweight and easily recyclable. Wood will predominantly be used in the frame and panelling of the interior of the ship. It is renewable, will be locally sourced and is fit for purpose. Insulating the boat is key for reducing energy consumption and keeping the vessel warm for passengers. We decided on sheep's wool due to its renewability, flame retardance and low weight. The floor will be laminate covered due to it being very easy to clean, recyclable and can also be cut to fit complex floor plans. We looked into several power sources to use for our ship and produced a matrix to show their advantages and disadvantages to help us decide which ones to further research. Many power sources do not meet our power requirements, so are disregarded straight away, even though they have some excellent properties and possibly in the future could be viable. At this time, we will not look into them any further. The first viable source is diesel, and it's what the current ferry uses. It produces a large amount of emission and is non-renewable, so is disregarded even though it does fit all the other requirements. A diesel engine converted to use a mix of diesel and biofuel is a good option because it halves the diesel needed but with all the advantages of the diesel engine. However, the engines will need a more regular service. Nuclear energy is not suitable for our ship due to its large size, high costs, radioactive waste and safety issues. Geothermal is our best option at the moment, producing more than enough energy than we need from a renewable source. However, this energy will need to be fed to the ship in some way. Liquid natural gas is expensive to set up due to the equipment needed, but running costs are far less than diesel. It uses large cryogenic tanks to store the fuel and produces little emission, but the tanks will need to be empty when the ship is not running for safety reasons. Another possible option is using mains electric from the national grid. Canada produces most of its energy from renewable sources like hydroelectric.
Biofuel is another one of the potential power sources that we are considering for our ships. A biofuel will be made using algae. The algae are extracted from the source, which will then be exposed to electromagnetism and pH change. This will break down its cell walls. This will release its slurry algae oil, which will be then directly converted to biodiesel using simultaneous oil extraction and transesterification. Algae can be grown very quickly and has the cost in the range of 42 to 97 cents per liter of biofuel. Using 70% to 30% mix of algae biodiesel to standard diesel ratio, the performance will be 3% more efficient than pure diesel itself, with no adverse effect on the engine. This, along with the reduction of sulfur by up to 80%, and the reduction of nitrous oxide by up to 30%, other hydrocarbons are reduced by 10%. Since algae also does photosynthesis, it takes up some CO2 when it is still growing. Standard diesel can be easily converted to run biofuel.
LNG is natural gas cooled to form liquid. At first, a large amount of electricity is needed to power on-site liquefaction gas cooling systems, but once it reaches the required temperature, it is stored in heavily insulated cryogenic tanks. There is, however, inevitable heat loss, causing vaporization or boil-off, and this is what's collected and burnt as fuel. Heat exchange systems can reduce the boil-off rate, but this fuel is stored as a boiling cryogen, meaning it doesn't want to stay in liquid state, so it continuously vaporizes and so must be continuously burnt. However, keeping the tanks at a constant pressure reduces the risk of ruptures, and means auto-refrigeration can occur, where a near constant temperature is sustained. LNG is insoluble and leaks will quickly evaporate. It is non-toxic and is highly unlikely to ignite outside the engine, and whilst using LNG is non-renewable, it may become possible to derive sufficient power from liquefied biogases. The methane content of natural gas means it carries the risk of methane slip, where unburnt methane can leak into the atmosphere. Another major concern is the need to establish sufficient bunkering facilities on site, which is where the engines are flushed with fuel at times of extended inactivity. Nevertheless, the fuel is becoming increasingly used by commercial vehicles.
Canada's west coast forms part of the Pacific Ring of Fire, which is a series of active volcanoes and earthquake zones. Canada's in-place geothermal power could exceed 1 million times Canada's annual electrical consumption. There are two major types of geothermal energy production considered for this application. The first is flash steam. Hot water heated to 182 degrees centigrade rises up in a well, and some of this becomes steam and is used to drive a turbine. The cooled water is then pumped back into the ground. In a binary cycle, water between 107 to 182 degrees centigrade is used to vaporize a working fluid which drives the turbine. The working fluid may be a low boiling point organic compound. The water is also returned to the ground.
The geothermal plant will be onshore and the electric power will be sent to the ship via a submarine cable. This cable will be weighted so it sinks down low not to affect other harbour users. There will be batteries on board the ship, but only as a backup system, just in case the cables get damaged in some way. Usually there will be a direct feed of energy going to the propellers, and this will reduce the amount of batteries needed on the ship, and therefore saving us a large amount of weight. There will be transformers on both sides of the cable. The voltage will increase whilst in the cable to improve efficiency, and then normalise again once it reaches the ship.
We will be utilizing lithium iron phosphate battery as a backup power source, just in case the connection with the main power plant is severe. It is perfectly suitable for our needs as it is very safe, reliable with no maintenance needed. Although it can be very expensive and cannot be overcharged, it won't be used very often since it has very high power to weight ratio. We only need about 3,100 kg for at most 3 minutes of travel time to the coastline. The excellent reliability means that this is the best battery for our needs.
A thin film of air bubbles are produced on the hull from air injection at the surface. Air is pumped through the holes to the bow, and as it disperses with the movement of the ship, the bubbles will spread and cover the hull. Likewise, a cutout in the hull, with the same principle of air injection, will form a pocket of air. This is then channeled either side of the propeller to disperse. This process will significantly reduce drag, with little additional power needed. Contra-rotating propeller systems can help in the recovery of rotational losses from the propeller, so improving efficiency. Singular rotating propellers will produce a swirling wake, which increases the drag. This is countered by the addition of a second propeller on the same shaft, rotating in the opposite direction. Pre-swirl stators can also be fitted, which, although being less effective, are far less complex to install. These are non-rotating fins with a diameter equal to the propeller that channel the water so that it swirls in the opposite direction to the propeller before passing through it. They can be fitted with a nozzle to further increase their efficiency. This slide shows the various designs we considered for our double-hulled catamaran. One major feature in all of them is the large proportion of glass, aiding in the maximisation of natural light. Also, it's a necessity that the crew captaining the ferry are able to maintain 360-degree vision at all times, so we needed a raised bridge. Also, we needed a design which didn't resist the air or water too much, so we sought current examples to reference from with good aero and hydrodynamics. We learned there should be no shear or rough faces or such, and as the ferry is operated with a cable system, the design should be symmetrical so that the same benefits are had when travelling in both directions. There are radical designs, such as 9, and some less so, such as 7, and it is 7 that the group decided to go for, due to being an efficient shape and likely to function well with the other design influences on our specification. This has been developed into a simple initial CAD drawing.
Now that we have proposed our research and basic design idea, we will next refine our design, create a detailed CAD drawing, and then write an in-depth project report, all to be completed by May. This is a Gantt chart to show our planned procedure for the next coming months. We are Group 13, and I hope you enjoyed our presentation.